Today, we're going to talk about mass wasting. So this chapter discusses the fundamental process driving mass wasting. Mass wasting. So mass wasting is the downslope movement of earth materials under the influence of gravity. So mass wasting principally involves soil materials, which are byproducts of weathering and erosion. So mass wasting occurs when the slope is too steep to remain stable with existing materials and conditions. Dramatic example of mass wasting occurs in mountainous areas and downstream valleys. So in other words, gravity is the driving force of mass wasting. Loose materials that flows down the slope under the influence of gravity, that is mass. To further elucidate, here is a video showing a mass wasting event. As you can see, it has a large movement of rocks, soil, and debris downward due to the force of gravity. So the Earth's outer crust is being wasted away on a massive scale and falling to lower elevation. It is a type of erosion and it is capable of making big changes of the side of a mountain. These changes can happen suddenly or it can happen more slowly over time. Slope stability. Slope stability is based on the interaction of two forces, driving forces and resisting forces. Driving forces move materials down the slope, most common, weight of the slope materials. Resisting forces oppose downward movement, most common, strength of slope materials. If resisting force is greater than driving force, the result is stable slope. If resisting force is less than driving forces, it results unstable slope, causing the slope failure. So in other words, slope failure occurs when driving forces overcome resisting forces. Force of gravity. So force of gravity is the driving force of mass wasting. It plays a part in mass wasting and it is constant on the Earth's surface for most part. Although small variations exist depending on the elevation and density of the underlying rock, in this figure, a block of rock situated on a slope is pulled down towards the Earth's center by the force of gravity. The gravitational force acting on the slope can be divided into two components, the shear or driving force, which moves the block down the slope, and the normal or resisting force, pushing the block into the slope, which produces friction. The relationship between driving force and resisting force is called shear strength. When the resisting force is greater than the driving force, then the block does not move downslope. However, if the slope angle becomes steeper or if the earth material is weakened, driving force exceeds resisting force, compromising shear strength and downslope movement occurs. In this figure, as it shows, the force vector change as the slope angle increases. The gravitational forces doesn't change, but the shear force or the driving force increase while the normal force or the resisting force decreases. So that is how force of gravity plays a part in mass wasting. Angle of repose is which the slope is stable and will not move downslope. It is the balance between the pull of gravity and friction, and the angle depends on the type of materials. Angle of repose, in the other word, is an angle that can be assumed by loose fragments on the slope without downslope movement of the material. It's essentially the battle between pull of gravity and a friction. Different materials has different angle of repose. As it demonstrated by the diagram below, it's hard to build a steep pile of a dry sand and it's easy to build steep pile out of gravel. As you can see in the diagram below, different materials, different sizes and shape of materials all have different angle of repose. If the angle of repose is exceeded, a mass wasting eventually will result. At this point, let us discuss the mass wasting triggers and mitigation. There are 4 common triggers of mass wasting that is important for you to know. Those are the following. First is water. Water which makes the soil heavier, causing it to move faster down the slope. Second is oversteepening slope, both by human and natural event. Third is removal of anchoring vegetation, again, both by natural or human cause event. And the last one is earthquake, violent shaking over an area. Increase of water content. So of all the factors that plays a role in erosion and therefore trigger mass wasting, increase of water content may be the most important. Water can both increase the risk of mass wasting and decrease the risk depending on how much water is present. This can be related to building a sand castle at the beach. In order to make a sand stick together, you need a little bit of water. However, if you add too much water to the sand, you will have a hard time getting the sand castle to stand up, and your sand castle walls will collapse under the influence of gravity. The same goes for soil particles on the mountain slope. A small amount of water helps them to bond and stick together. If too much rainfall, soil becomes saturated by increased water, then soil particles and other materials will wash away down the mountain. Increased water content within the slope is the most common mass wasting trigger. Why? It is because water is heavy, so it adds weight. The water is lubricant, so it reduces friction. Thus, the gravitational force is increased due to the weight and the friction force is decreased due to the lubrication. Many mass event occurs right after or during heavy rain event. So most landslide mitigation diverts and drain water away from slide areas. Tarps and plastic sheeting are often used to drain water off the slide bodies and prevent infiltration into the slide. Drains are used to dewater landslide, and shallow wells are used to monitor the water content of some active landslide. Overstepping is also one factor that trigger mass wasting. Overstepping occurs when the slope exists at a stable angle. Overstepping can happen by natural means such as undercutting by a stream or by wave action. It can be human-caused such as overstepping the cut slope during forms of development. Here's a photo of overstepping directly caused by human activity. This before and after photo is intended to show what happened when overstepping slope occur. As you can see, the steep cut area are overstepping. Thus, it creates mass wasting occurring both above and below the home site. Overstepping triggers both natural cause events and human cause events. Mitigations such as slope reinforcement help mitigate mass wasting, just like in the city road here in Iligan. You can see reinforced steep slope by confining soil and filling material while allowing slope drainage and help promote healthy vegetated slopes.
Thank you, Missy, for that wonderful and very informative discussion. Now, let's move on to the different parts of a landslide. At the very top, we have the crown, which is the undisturbed material uphill the scarp. Next is the main scarp, which is the steep slope at the upper edge of the landslide, just below the crown, caused by movement of displaced material away from the undisturbed ground. This is the visible part of the slide surface. Then the flank. This is the undisplaced material adjacent to the side of the landslide. Compass directions are preferable in describing the flanks, but if left and right terms are used, then they refer to the flanks as viewed from the crown. The main body, the part of the landslide that overlies the rupture surface. The rupture surface of the surface of rupture is the lower boundary of the movement below the original ground surface. This is the surface wherein the material slides. Tension cracks found in the middle of the slide formed as the result of the middle part of the slide being pulled up. Separation surface, part of the original ground surface that is now covered by landslide material. Foot, part of the landslide that overlies the original ground surface or the separation surface. And lastly, we have the toe, the downhill end of the slide, and the most distant part of the slides from the main scarp. Next, let's tackle the classification of mass wasting process, the different types of mass wasting, as well as the different examples of mass wasting or landslide. People usually use the common umbrella term landslide when talking about the different mass wasting events, but there are specific and easy naming system. There are two criteria to classify mass wasting events. First is the type of material involved, which consists of debris, mud, earth, and rock. Second is the type of motion. When a material free falls, we call it fall. If the material slides or moves along a surface, it's called slide. Surface in here refers to the joint, fault, bedding plane, or curved surface. But if the material moves like a viscous liquid, it's called a flow. And lastly, creep, which is a very slow and gradual movement of a material. Then, to name a mass wasting event, you just have to take the type of material and combine it with the type of motion that you see. For example, if a debris flows, then it's called a debris flow. Or if a rock falls, then it's a rock fall. Simple, right? This is a simple naming process, but we must remember that these catastrophic events are not simple and needs a lot of knowledge, examinations, as well as different circumstances taken into account during the naming process. This process is just to simplify the complex nature of these catastrophic events. Now then, let's move on to the specific types of mass wasting. First, we have rockfall, the most common mass movement. Rockfall usually occurs from abrupt rock movements that detach the material from steep slopes or cliffs. These are usually caused by mechanical weathering, bedrock fractures, and glaciation. An example of this mass wasting event is the rockfall that occurred at Barangay Canipa, Tinambacan District, Calbayog City, Samar. It was brought by the Tropical Depression Agaton at January 3, 2018 at around 2 a.m. Fortunately, there were no casualties and only one light post and an inhabited house were the only loss suffered. Next is the rotational slide. In this slide, the surface of rupture is curved concavely upward, and the slide movement is roughly rotational about an axis that is parallel to the ground surface and transverse across the slide. The August 2014 North-South Lake landslide is an example of a rotational landslide, specifically a slow-moving rotational landslide. These mass waste managed to destroy one home and damage nearby tennis courts. Then we have translational slide. This mass waste moves on a roughly planar surface with little to no rotation or backward tilting. It can also progress over considerable distances if the surface of rupture is sufficiently inclined. As you can see, the September 2018 Naga landslide is an example of this mass waste. It was said that the area that collapsed was due to the extensive mining. Various concerns on the instability of the area has also been raised prior to the event. As you can see within the screen, this is roughly the difference between rotational and translational slide. Rotational slide's surface of rupture is spoon-shaped or concaved, while translational moves on a planar or the plane surface. Then we have the creep. This is the slow downward movement of materials, usually caused by earthquakes, heavy rainfall, permafrost thawing, or the regular cycle of nighttime freezing followed by daytime thawing in unconsolidated materials such as soil. An example of this landslide is the Vaillant landslide in 1963. It was said that during the construction, the chief engineer of the dam was already concerned about the stability of the left bank, as compiled reports have shown that there has already been a prehistoric slide on the right bank. But the concern was promptly dismissed. Due to this, more than 2,000 people died due to the wave that a 270 million cubic meter rock caused when it slid into the reservoir at 3 meters per second. Lastly, we have mudflow, a very fast and destructive landslide that consists mostly of soil and a lot of water. Mudflow is usually caused by heavy precipitation and rapid snowmelt. But before I discuss the given landslide example, let us first tackle the difference between mudflow, earthflow, and debris flow. The first picture is an example of a mudflow. The photo is taken at Legazpi City, Philippines, 2018, when the Mayon volcano was active in Albay. Due to the heavy rain at that time, people were fearing for their life as they are afraid that the rain will mix with the lahar that the Mount Mayon was spewing, risking a lahar flow. The next picture is the 2006 Kuinsaugan landslide in southern Leyte, an example of a debris flow. This is when the mud, during its movement, picks up trees, rocks, and debris, etc. And third picture, lastly, is the earth flow, which usually forms in hillsides in humid regions. It oozes slowly during or after heavy rainfall. And that's it. Thank you for listening, everyone, and I hope you learned and enjoyed the discussion.